Hi guys, my name's Arnav Sinha, and the goal of today's video is to educate you guys on Unit 1 of AP Chemistry. I'm currently a rising senior at Westview High School, and I took AP Chemistry as a junior, and I quite liked the class, which is why I'm making this video to teach you guys about it. So let's get into it. Now on the first slide here, I've just put an image of the periodic table with all the metals, non-metals, transition metals, and noble gases, and all the different subgroups of elements. And I guess what I'm just trying to say is really look at the periodic table and get a good feel for it. Because on the AP exam, when you're given a periodic table, it is better to just know where the elements are than to just go around hunting for them, probably wasting like an extra 2 to 4 minutes, which could have been used otherwise on actually solving the problems. So yeah, just keep looking at the periodic table, appreciate it, and it'll really help you on the AP exam. Let's move on. I'm pretty sure that many people who are taking AP Chemistry have taken STEM chemistry in the past, but there might be some exceptions. So I wanted to start with a small review first of basic chemistry. So an atom is made up of protons and neutrons in the middle, with electrons that orbit it. The protons and neutrons form the nucleus, and the nucleus is like a huge chunk of the mass of an atom. That is because while a proton and neutron weigh a lot, in terms of, they still don't weigh too much, like not as much as us, of course. They weigh little, but comparatively to electrons, they weigh way more. And since electrons weigh virtually nothing, they're not a part of the atomic weight. Like not a huge part is what I'm trying to say. So just know that. And also electrons orbit the nucleus in a sort of shell fashion, and electrons that are in the outermost shell are known as valence electrons. This will come in more handy later in the video. And what I've done here is I've just pulled up a representation of one element on the periodic table. Here we have arsenic, which is my favorite element because I just think it sounds cool, and it is pretty cool too. In the top left corner, you got the atomic number, which is just the number of protons in the element you're looking at. And in the top right, you got the average atomic weight. Now, the reason it is average atomic weight and not atomic weight will be looked into later in the video, but just know that's like a rough estimate of how much one atom of that element weighs. Now, at the bottom, we have the name, arsenic, pretty cool. And electron configuration, which is another concept that we will look at later in this video. That's just like the basics of how to read an element on the periodic table. Now let's move on to some new stuff. What is a mole? A mole is a unit of measurement that scientists have like used and written all over the periodic table that tells you how many grams of something are in 1 mole of something. So for example, it's similar to how we know a dozen is 12, so like we know a dozen of donuts is 12, or how a baker's dozen is 13. Similarly, we know how many grams of one element are in 1 mole of that element by looking at the periodic table. Now, let me just give some examples real quick. So down here, 1.008 for hydrogen. So we know that 1 mole of hydrogen has 1.008 grams of hydrogen. That's the conversion that scientists have set up. So you don't need to memorize anything. It's all here on the periodic table. You just need to look underneath the element's name. Let's do another example. Nitrogen, 14.007 grams. So we know that 1 mole of nitrogen is that many grams of nitrogen. It's just a unit of measurement that we use. Now we got Avogadro's number, and this dude Avogadro, right? What he basically did was he came up with a number for how many atoms of one element are in 1 mole of something. And this is the same for all elements. So in 1 mole of hydrogen, there are 6.023 times 10 to the 23 atoms, and it's going to be the same for nitrogen. There's going to be the same number of atoms in 1 mole of nitrogen, or helium, or xenon, or anything. So that number always stands. And the process through which we solve problems in chemistry and can't like come up with an answer is known as stoichiometry or gravitational analysis. So we will look at examples later, but basically the gist of it is you organize stuff in a fraction sort of format, and then you cancel out units until you end up with the units in which you want your answer. Now, my chemistry teacher even said that you can use this in physics. So yeah, it really might be worth learning what it's about and how to do it, because it could help you in other classes too. So let's start with an example conversion. So I will give you the average atomic masses, so you don't have to like look at the periodic table. So how many grams of oxygen are in 3.00 moles of oxygen? So the average atomic mass of oxygen is 15.999. So what we first do is we write down the 3 moles of oxygen, okay? And here's where the fraction part comes in. We know that for every 1 mole of oxygen, there's 15.999 grams of oxygen from the periodic table, the average atomic mass. Yeah. So our goal is to end up with grams, right? Because it's asking for grams. And in order to do that, we want the moles to cancel out. So we end up with grams. So what I've done here is I've written down 3 moles of oxygen, and then I've put moles in the denominator so that it cancels out with the other moles and you're just left with grams. So when you multiply 3 by 15.999, you end up with approximately 48.0 grams of oxygen. And that's our answer. That's how many grams of oxygen are in 3 moles of oxygen. Now our next question is how many atoms of nitrogen are in 4.00 grams of nitrogen. Now this is where we are going to use Avogadro's number alongside the other operations we did in the first example question. So of course, we'll start with 4 grams of nitrogen, and then we're going to put grams in the denominator this time because we want the grams to cancel out, right? Because we want to end in atoms, of course, but that's like a later step, but we want the grams to cancel out as of now. So the grams of nitrogen cancel out, the grams of nitrogen cancel out. That's 1 mole. And then Avogadro's number states that there are 6.023 times 10 to the 23 atoms of any element in 1 mole of that element, right? So similarly, in 1 mole of nitrogen, there's going to be that many atoms of nitrogen. Now, we're going to put moles of nitrogen in the denominator, so they cancel out with these moles, and we end up with atoms. Now, once we multiply everything out and everything cancels out, we end up with approximately 1.72 times 10 to the 23 atoms of nitrogen. Pretty cool stuff. Now, I have a third example too, but in this case, I don't have an atom, I have a molecule. So we have ammonia, which is NH3. Now, before I show the answer, I want to explain how we actually get the atomic mass of ammonia. Because if we go back to the periodic table, right, there's no ammonia on here. There's just elements and atoms. So first step is to like figure out what the formula is for the molecule. Ammonia is NH3. And then basically what you just do is you add up all the atomic masses of each individual atom. So N is 14.007, and since it's H3, that means we have 3 hydrogen atoms. So we're gonna add 1.008 times 3, because there's 3, plus 14.007. And that's basically how you find the atomic mass of any molecule. And if we just do what I just said, we end up with 17.031 grams of ammonia for every 1 mole. Not that hard, right? So then we start with 16.2 grams of ammonia, and then again we put grams of ammonia in the denominator because we want it to cancel out as we want our answer in moles. And we end up with 0.951 moles of ammonia. Yay! Alright guys, so the next topic that we're going to be looking at is isotopes. So what is an isotope? An isotope is basically a variant of an element where the factor that changes is the number of neutrons. So every element has like a base form, and if you were to like add or subtract neutrons from that, that would create an isotope. And isotopes really naturally occur, so I don't think humans can create isotopes, but I mean, we probably could, but what I'm trying to say is they more commonly occur naturally, right? Here's an example. We got carbon 12, 13, and 14. So carbon 12 is sort of the base form with 6 protons and 6 neutrons. Carbon 13, on the other hand, has 7 neutrons, and 14 has 8. So carbon 13 and 14 are going to be the isotopes. Now, I remember talking about this earlier, but I want to explain why we look at the average atomic mass and not just the atomic mass. So now that you know isotopes exist, it would be pretty unfair, right, to just look at one version of each element and assign that as like the atomic mass. Well, that is why we look at the average atomic mass, because we need to look at each individual isotope, its abundance in nature, and how much they each weigh to come up with an average. If we just assign one isotope's mass to the whole element, that's just not fair. You're not accounting for everything. So that's why the average atomic mass exists. I have 2 quick disclaimers real quick. Noble gases, so all those dudes on the right, they don't have isotopes, right? Because they refrain from reacting with other atoms or molecules, And you can just like kind of remember, right? The name is noble gases, so they're kind of noble, right? They don't react with any other elements or atoms. And then we got the difference between average atomic mass and atomic number. So in my class, there were some people who confused the two, so I just want to like clear this up. Average atomic mass is how much each individual atom weighs, while the atomic number is how many protons each individual element has, right? So yeah, don't make the same mistake those other dudes made. Yeah, including me. So what is mass spectroscopy? You're just basically implementing what we just learned about isotopes into like a graphical form. So I'm just going to show you a few examples and let's get on with it. So let's look at silver first, right? That's silver's mass spectroscopy diagram. So as you can see, there's two isotopes, one that weighs 107 mass units and one that weighs 109 mass units. So you might be wondering why the average atomic mass of silver is not just 108, right? Because it's in the middle, makes sense, it's the average. What you are forgetting and what you're overlooking is the abundance. So if you look closely here, the abundance of the isotope that weighs 107 is higher than the abundance of the one that weighs 109. This is why the average atomic mass leans a bit more towards the isotope that weighs 107. So that's why it's 107.87 and not 108. Let's look at another example, which is boron. Boron also has two isotopes, but in this scenario, the difference in abundance is huge. Like, just look at that. The isotope that weighs 11 mass units has an abundance of 80%. That means every 4 out of 5 atoms of boron in nature are of that isotope, right? So that is why the average atomic mass is 10.811, because they'll lean more towards the atomic mass of 11 than to 9, because the isotope that weighs 11 is more abundant, right? So that's why it's 10.811. Now I want you guys to try, just give it a shot. Let's see how I'm teaching. So here's a graph of the element whose mass spectrometry chart I've given, and I want you to guess what element it is, right? Here are your 4 options. So you got magnesium, oxygen, sodium, and cobalt. And I've given you the average atomic masses, so it's easier. Also, just ignore the blue boxes on the chart because they kind of give away the answer, so I just wanted to kind of censor it so you guys really had the chance of trying and learning. So I'm just gonna give you guys some time. Just pause the video and try, right? Okay, I'm assuming you guys have paused the video and tried, and the answer is magnesium. So for those of you wondering why it's magnesium, or for those of you that already got it, good job. It's magnesium because magnesium has an average atomic mass of 24.305. And if you look at the chart, the isotope that has a mass of 24 mass units is the most abundant, 79%. So we, off the bat, know that the average atomic mass is going to lean towards 24 or be around 24, right? So that's why magnesium is a pretty good shout. It's pretty close to 24. Oxygen, on the other hand, has an average atomic mass of 16 approximately. That's not even on the x-axis, so you can automatically avoid that. Like, it's way far to the left. Same thing with cobalt. Cobalt's 58.933. It's way far to the right, so you can just avoid it. And while sodium's like a semi-decent option, it's wrong because the average atomic mass it indicates is 22.9, which is to the left of 24 units, right? Because it's less than 24. And that doesn't make sense because we're looking at a range between 24 and 26 mass units because those are like the range of the isotope weights. So that's why sodium is wrong as well. All right, guys, for the next portion of our video, we're going to be looking at pure substances, right? And pure substances are basically just molecules. We're looking at a slightly larger, and we're moving from atoms to molecules, right? So there are 3 main ways to denote such pure substances in chemistry, right? We got the empirical formula, the molecular formula, and the structural formula. So the molecule we're looking at is methane in this case, which is CH4. So the empirical formula is like the most baseline, most basic way to write a molecule. So CH4 is methane, so that's its empirical formula. The molecular formula is sort of like a more, it's the empirical formula, but you're kind of multiplying each atom by, I guess, a certain number. So in this case, molecular formula C2H8, you can simplify that to CH4, right? So that's another way you can think of it. The molecular formula is an unsimplified version of the empirical formula. And yeah, The third one is the structural formula, which is not as important in this unit. In later units, you'll do like bond angles, Vesper, and all that, and that's when that really comes into play. But just if you guys are curious, that's how methane looks. You got 4 hydrogens around that 1 carbon, and then you got those bond angles, which we'll do in the future. Now, I've got some example problems, so let's get on with it. We have to calculate the empirical formula in a sample that's 50% sulfur and 50% oxygen. Now, this might look really daunting. I know it did to me. So let's walk through this one, right? So what I want you to do first in these kind of problems, it's really helpful, is, oh, that's the periodic table if you guys needed it. Just assume that like the sample weighs a certain amount. In this case, I've used 10 grams. You can use 100, 1,000, anything that's like divisible and nice to work with. So I've used 10 in this case. So our sample weighs 10 grams. Since it's 50% sulfur and 50% oxygen, I just assigned 5 grams of the sample to oxygen and 5 grams of the sample to sulfur. And then all I did was I converted the grams to moles. That's the first step in these kind of problems. So 5 grams of oxygen, again using the molar mass of 15.999 for every 1 mole. Grams cancel out, you get 0.313 moles of oxygen. Same thing for sulfur, the grams cancel out, you get 0.156 moles of sulfur. Now the next step is you want to divide the larger mole value by the smaller mole value. So let me show you what that looks like. So in this case, the larger mole value is 0.313 because 0.313 is greater than 0.156, right? So that is why we're going to divide it, and we get approximately 2 moles of oxygen, and then we divide 0.156 by 0.156, and we get approximately 1 mole of sulfur. So that's why in this case, the empirical formula is going to be SO2. Now, if you think about this, I know some of you are probably wondering why we divided, right? In a sense, that's kind of like, oh, sorry, I'm using my finger. That's kind of like another molecular formula, but it's in decimal form. So 0.313 and 0.156. You could write like O 0.313 and S 0.156, but that's just like weird because we don't use decimals as our subscript, right? So by dividing them, we're coming up with whole numbers that serve the same purpose and come up with an empirical formula. Let's look at another example. Calculate the empirical formula of a sample that is 40% oxygen, 40% sulfur, and 20% helium. Same thing this time. We're gonna start off by setting a mass quota for the sample at hand. So there's a periodic table. In this case, I use 10 grams again. And since we have 40% oxygen, 40% sulfur, and 20% helium, that's 4 grams of oxygen, 4 grams of sulfur, and 2 grams of helium, right? And once again, you start by converting it to moles. So 4.0 grams of oxygen, the grams cancel out. So that's 0.250 moles, and then 0.125 moles of sulfur, and then 0.500 moles of helium. So once you have all these mole values, again, you're going to divide all of them by the smallest mole value. In this case, it's sulfur, which is 0.125 moles of sulfur. So when you divide it out, you come out to 2 moles of oxygen if you divide 0.250 moles, 1 mole of sulfur because you divide it by itself, and then 4 moles of helium because 0.5 divided by 0.125 is 4. So that's why in this case, your empirical formula is going to be He4SO2. Just a quick disclaimer, I am not 100% sure that that molecule exists. It's just an example problem, guys. So I am not guaranteeing that molecule exists. Okay, let's move on. Oh yeah, I have a tip too. When you're writing the empirical formula, even on tests, this is quite helpful. My teacher told it to me. You want to go from the least to the most electronegative. This really helps, and this is kind of how scientists and chemists in general write the formula. And if you use this tip, you're very likely to be correct in your empirical notation. Now I have a third problem. So many problems. Now, this one's a bit more different. You're looking at individual atoms and molecules, right? So let me just read it out. The combustion of a molecule produces 110 grams of carbon dioxide and 66.0 grams of nitrous oxide. If the original molecule only contains carbon and nitrogen, find its empirical formula. Again, looks very daunting, right? But let's break it down and solve it. You got a periodic table again. This time I'm actually going to explain with the periodic table because it's a different type of problem. So let's deal with carbon dioxide first. So we have 110 grams of carbon dioxide. So you want to always convert to moles first in these kind of questions, right? So if we convert to moles, we cancel out the grams and we are like 1 mole at the top. And our next step is, since it's saying the original molecule only contained carbon and nitrogen, We want to find the moles of carbon in CO2, not the whole thing, right? Because we're focusing on that carbon. So that's why we say in 1 mole of CO2, there's 1 mole of C. Because if you look at the empirical formula for carbon dioxide, there's 1 mole of carbon and there are 2 moles of oxygen. That is why you have 1 mole of carbon for every 1 mole of CO2. And once everything cancels out, you're left with moles of carbon, and you have 2.5 moles of carbon. So we know how many moles of carbon there are. Like, we're going to do the same thing with nitrous oxide, right? We have 66.0 grams. We're going to convert to moles, so the grams cancel out. And then in this case, for every 1 mole of nitrous oxide, we have 2 moles of nitrogen, because as you can see from the empirical formula, there are 2 moles of nitrogen, right? And once everything cancels out, we're left with 3 moles of nitrogen. Now, remember how in the last case I told you to divide? In this case, if you were to divide 3 by 2.5, you would come up with a decimal, right? So it would be simpler in this case to just multiply it out. So if you do 2.5 times 2, you have 5, and then 3 times 2 is 6. So the original molecule is C5N6, which is also known as 2-diazo-4, 5-dicyanoimidazole. Yeah, it's a really long name, but that's the molecule you come up with. And it might seem confusing when to divide and when to multiply, but it's really up to personal preference, and you kind of know when to do it, right? Because as you do more of these problems, you will realize that if you have 2 numbers and you divide by the smaller one and you end up with another decimal, you're not going to do that. So you just multiply it out to a point where you get 2 whole numbers. So that's how you solve this kind of problem. All right, guys, the next topic we're going to be looking at is mixtures, which is very similar to the pure substances concept we just went over, except we're looking at individual atoms in like a whole molecule, right? The questions here are kind of similar to the one we just solved, but of course they're a bit different because it's a different part of the unit. So one major concept within this sub-concept I wanted to go over is cross-contamination. Now, I'm going to give you 2 scenarios to explain this. So let's say you have a solution of NaCl, which is just salt, right? And you put it in water, and then you add some HCl to it. What do you think that's going to do to the percent composition of chlorine in the solution? Now, if you said it's going to increase, you're correct, because by adding HCl, you're effectively adding chlorine, because chlorine is a part of HCl, right? And therefore, you're increasing the percent composition of chlorine within the whole solution. There's another example. Let's say you're adding more water to a sample of sodium chloride that's already in water. So what does that do? So if you said that decreases the concentration of chlorine, you're correct again, because you're decreasing the amount of chlorine that's in the whole solution by adding more water, right? Because let's say you have 3 grams of sodium chloride and you had like 2 grams of water from the start, just the base solution, and you add like 5 more grams of water. That decreases the total amount of chlorine in NaCl that's in the solution, and therefore it decreases the percent composition of chlorine. Now, this is a pretty neat concept that you can use in lab reports, right? Because when you're using the lab report and you come to the error analysis part, cross-contamination is a pretty common source of error. In like a lot of the labs I did in AP Chemistry, this was a pretty common source of error that I used, and it was also pretty relevant to the lab. It was not like I was just making something up. It came up a lot. So yeah, it's worth learning about. And also another thing I wanted to point out is that this percent composition concept is kind of under the broader category of molarity and concentration, which is something we'll cover in future units. So don't worry about it too much as of right now. So I've got some example problems. So let's say that a compound weighs 12.2 grams and it has the form compounds, calcium carbonate and magnesium sulfate. And we already know off the bat, this was just given to us, that it contains 0.05 moles of magnesium sulfate. So we want to know what is the percent composition by mass of MgSO4 in the whole solution. So we are given magnesium sulfate's atomic mass, which was just by adding the individual atomic masses of each atom, right? As we did in the previous questions. So our first step is going to be to convert the 0.05 moles of magnesium sulfate to grams of magnesium sulfate, right? Because if we're going to take the percent composition, we need to convert it to grams, right? That's the first step. So in this work here, the moles of MgSO4 cancel out and we just have 6.02 grams of magnesium sulfate. And then the last step is just putting the grams of magnesium sulfate over the grams of the overall compound. And then you have your percent of magnesium sulfate, which is 49.3%. And then I have another question. A giant sea salt chip weighs 10 grams and contains 0.1 moles of acetic acid. And the question is basically asking, what is the percent by mass of acetic acid in the chip? Now, overlooking the fact that this chip weighs 10 grams, we will start by converting the moles of acetic acid to grams again, just like we did in the previous question, right? Because in the end, if we're trying to find percent composition, we're going to put those grams over the overall grams times 100, right? So when we convert to moles, the moles cancel out. And when we convert to grams, the moles cancel out, and we are left with 6.01 grams of acetic acid. And what we do then is we put the grams of acetic acid over the overall grams times 100, and we come up with 60.1% of acetic acid in the whole solution. So that is its percent composition in this giant chip. Okay guys, so the next concept we're going to be going over is electron configuration. And throughout my time in AP Chemistry, this was perhaps the most difficult concept in Unit 1. But after like a lot of practice and just like learning the order of stuff, it just clicked and it wasn't that bad after that. So I'm hoping that through this explanation and the couple of examples that we're going to do together, you guys can get a good feel and grasp for how to write down electron configuration. So firstly, I've put up the electron configuration for arsenic down, and it might just look like numbers and letters right now, but it will make sense by the end of this explanation, hopefully. So what is electron configuration? It is basically the process through which we represent the different electrons that resonate with every individual element on the periodic table. And you might just think they rotate in plain circles, but it's a bit more complicated than that. So I would just like to demonstrate real quick what's the difference between an electron shell and an electron subshell. So firstly, in this diagram, right, these concentric circles, each circle is an electron shell, okay? And within each shell, there are subshells, okay? And on the test, sometimes they use different terminology. So an electron shell, like each layer, is also known as an energy level, and subshells within the shell are also known as orbitals. So just keep that in mind. So yeah, an electron shell is the actual like circles, figuratively, not actually, and then subshells reside within the shells. So that's what I was trying to explain real quick. All right, going back to our presentation. So of the subshells, there are 4 different types. These are where the electrons are actually stored, and they are the S subshell, the P subshell, the D subshell, and the F subshell. Now the S subshell only holds 2 electrons, the P holds 6, the D holds 10, and the F subshell holds 14 electrons. Now the electron shells, or the subshells, subshells do not always have to be full when you're writing down your electron configuration, because depending on the element on the table, they have a different number of electrons, right? And therefore, the subshells don't always have to be full. So let's do an example to explain it. Oh, before that, here are 2 methods I learned of. So the first one, the one on the right, is like a beginner sort of one that I would urge you to use towards the beginning. So this is something I found on the internet, which was really helpful when I was learning. So basically, what it does is it has arranged all the like different subshells, and the arrows kind of show in order. So you start with 1s, then you go to 2s, then 2p, then 3s, then 3p, then 4s. So you just follow the gradient of the arrows, and that is the order in which you write down the electron configuration. And then just to clear this up, to find out how many electrons an element has, you just find the element and then you find its atomic number, because the number of protons is always going to be equal to the number of electrons. So let's say you're looking at, I don't know, oxygen, right? Its atomic number is 8. So its number of electrons will also be 8. So therefore, you're trying to have 8 electrons in the electron configuration. All right. And the periodic table method I was trying to show is that the periodic table is structured in a way that is really intuitive and helps you fill out the subshells. So let's start. So for this method, you want to treat every element like an electron, right? So if you treat hydrogen and helium as electrons, that's 2 electrons. That is the 1s subshell, if you think about it. And then lithium and beryllium, if you treat them as electrons, that's the 2s subshell. And then boron through neon is the 2p subshell. And then sodium through magnesium is the 3s subshell. And then aluminum through argon is the, I believe, 3p subshell. Yeah, and then you just keep going like that. And it follows the order. And that is basically how you have to, over time, learn to do it without the diagram on the right. But if you really want to, and you really don't want to learn this method, on the test you could just draw that diagram on the right, but it's a bit on the time consuming side, so that's why I would recommend using the method on the left and actually learning the way the periodic table has these subshells organized within itself. Okay, so this is some practice that I'm going to do with you guys. All the questions for this we're going to do together because it's pretty hard. So let's start with writing the electron configuration of oxygen. So I have pulled up the diagram on the left and the periodic table on the right, and I'm going to explain it in both means. So first we're going to find the oxygen atomic number, which is 8. So we know it has 8 electrons, and therefore we need to have 8 electrons in the electron configuration. So that is the answer, and the reason I've given you the answer is to actually show you how to notate it. So we know that the s orbital holds 2 electrons and the p orbital holds 6 electrons, right? When it's full at maximum capacity, it doesn't have to. So using the diagram on the left, this is for beginners. I'll explain it via the periodic table method in a bit. But you start with the 1s subshell, so that's 2 electrons, it's full. Then you move on to the 2s subshell, fill it with 2 electrons, and then you move to the 2p subshell. But since oxygen only has 4 electrons, you will only fill it with 4 electrons. Even though it can hold 6, you only put in 4. And then you end up with 1s to the 2, 2s to the 2, 2p to the 4, right here. So the exponent is basically denoting how many electrons you're putting in the subshell. And yeah, that's what that means. A good way to check whether you're right or not is adding up all the numbers in the exponents and seeing if it equals the number of electrons in the element you're looking at. So oxygen has 8 electrons, and then 4 plus 2 plus 2 is 8. So in this case, we are correct. Let's do one for aluminum. So again, we got the 2 diagrams. In the case of aluminum, we are looking at 13 electrons because the atomic number is 13, 13 protons, 13 electrons right here. And so we're gonna once again fill up the 1s orbital fully, that's 2 electrons. We're gonna fill up the 2s fully, that's 4. We're gonna fill up the 2p fully this time, so that's 6 more. So 6 plus 2 plus 2, how many we got? We got 10 so far. We fill up the 3s fully, so we fill up the 3s fully as well, and we have 12. And then in the 3p subshell, we put 1 electron, and then we get 13, and that's the number we're looking for. Now let me explain this from a lens of the periodic table. So as I said, treat each element as an electron, right? So we got the 1s subshell from hydrogen, helium, so that's full. The 2s subshell from lithium and beryllium, that's also full. 2p is boron through neon. We're still not aluminum yet, so as before, if we're not at the element we're looking at, we're just going to keep on filling the orbitals fully. So boron through neon, we're going to completely fill it. So the 2p subshell is also full. And then we move on to the 3s, which is also full. But then as we make our way into the 3p subshell, we're only going to put in 1 electron because we want to be at aluminum, right? So that is our answer. 1s2, 2s2, 2p6, 3s2, and 3p1. And another way this is organized, if you think about it, the organization here, this whole column on the left with hydrogen, lithium, beryllium, sodium, these are all sort of the s subshells, okay? And if you look, except the top, the hydrogen helium is the only exception because it's kind of weird. Those are the 1s ones, but 2s, 3s, 4s, 5s, 6s, 7s, it's all in order. And then if you move on to the p subshells, that's also on the far right. If you look, boron through neon, that is 2p, aluminum through argon, that's 3p, then 4p, 5p, 6p. So that's the order. And then when you finally, you move on to the D subshells, so scandium through zinc is 3d, yttrium to cadmium, 4d, and then 5d, 6d. And then when you move on to F, that is these separated ones at the bottom. This is 4f and this is 5f. Now, they won't really go too far, really far towards the bottom of the table. But if they do, there's a method that is easier than writing down everything because, as you can imagine, it's going to be really time consuming to just write all this stuff out. And that is noble gas notation, which we're doing on the next slide. All right, so this is noble gas notation. It is way easier than just writing it down. So let's say, for example, in this case, they've given us barium. Barium's all the way here. So as I just mentioned, writing everything out is really time consuming. And therefore, noble gas notation basically just requires you to know the way the periodic table works in terms of subshell locations, like I just talked about, with like this being the S subshells, this being the P, this being the D, right? So we start off by just writing the closest noble gas before the element in square brackets. In this case, since we're looking at barium, the closest one is xenon. So we'll put xenon in square brackets, and then we just write out the remaining electron configuration after that. So in this case, it's 6s2. Remember the method I taught you. So this is 1s2, then this is 2s2, sodium, magnesium 3s2, potassium, calcium 4s2. This is 5s, and then we come up to 6s, and barium is 6s2. That is how we know it's 6s2. And this is why I really urge you guys to start with the one on the left, but then move the method on the left with the arrows, but then move on to the right, because if you're asked a question about noble gas notation, really knowing the order of subshells on the periodic table is really helpful. It saves a lot of time. And let's do another one with rubidium. So in this case, I'm just going to use the periodic table to explain it. So rubidium is located over here, number 37, atomic number 37. So the closest noble gas before rubidium is krypton. So we're going to put krypton square brackets, and let's see which S subshell it's in. Because since it's here, we can, on the left in these categories, we can assume it's in the S subshell. We have to find which one. So this is 1s, 2s, 3s, 4s, 5s. So we know rubidium is in the 5s subshell in terms of electrons. And we also know it only has one electron in the 5s subshell because it's not like, it's in this like period, it's in the first period. So that's why we are gonna write a krypton in square brackets and 5s1. And if you guys don't wanna like manually count the what subshell it's in, there's numbers on the left here too. I'm not sure if they're on the AP tests periodic table, but it could be pretty helpful to just write down these numbers because they will help you identify which what's like the number or what's the energy level on your subshell that you're looking at. Like, is it 1, is it 2, 3, 4? So that's really helpful. And then finally, one special variant of electron configuration I wanted to look at was when they ask you to write the electron configuration for an ion. So an ion is basically just any element's atom that has a charge associated with it. So let's do an example. It's pretty intuitive. So let's say we're looking at Mg3+, all right? So Mg3+ means that if you add a 3+ charge, that's the same as removing 3 electrons, right? Because the 3+ gets rid of 3 electrons because it's a positive. They like counteract with each other. So basically what that means is find the number of electrons magnesium has and remove 3 because there's a 3+. So in this case, magnesium's atomic number is 12. And since it will have 12 electrons, we're going to remove 3 electrons and end up with 9 electrons. Yes, that's correct. And since we have 9 electrons, we use the same method we've been using for electron configuration and just write the electron configuration for an entity with 9 electrons. So we start with 1s. So 1s orbital is full. So 2. So we have 1s2. And then 2s is also full, 2s2. And then the 2p subshell is going to have 1, 2, 3, 4, 5 electrons because remember, due to the 3+ charge, magnesium is going to have 9 electrons now. As you can see, that is the same. And similarly, if you have an ion with like a negative charge, you're just going to add electrons. So let's say you have a carbon 2-, okay? So normally carbon will have 6 electrons, but due to the 2-, you're going to add 2 more, and you're going to write the electron configuration with 8 electrons instead. Now let's move on to photoelectron spectroscopy. So what this diagram basically is graphically representing the subshells of any given element. And in order to do that, you need to know what ionization energy is. So ionization energy is basically the amount of energy that is required to remove the valence electron of an atom. And we know that valence electrons are on the outermost shell, right? So let's look at an example for oxygen so I can explain this further. But As you can see, the closer an electron will be to the nucleus, the harder it will be for it to get removed, right? Because it is closer to the nucleus and therefore more attracted to the nucleus, right? So that is why more energy will be required the closer it is to the nucleus. However, valence electrons will require comparatively less energy to remove because they're farther away and therefore they're experiencing a lesser attractive pull. We'll go deeper into this on the next slide with Coulomb's law, but for now, let's just go with this. So the farther away from the nucleus you are, the less energy it requires for you to be removed, right? So in this case, our oxygen's electron configuration is 1s2, 2s2, and 2p4, as you can see here. And so since on the y-axis is number of electrons, that's what we're representing here. So we have the 1s2 peak, we have the 2s2 peak, and then we have the 2p4 peak. Now, and the interesting thing is the x-axis. This is what I used to get confused over a lot, but as you can see, the left, the binding energy is the highest, and on the right, it's the lowest. And this makes, and the reason the 1s2 peaks closest to the left is because it's closest to the nucleus, right? Like I told you, the closer you are to the nucleus, the more energy it requires. And that's the same as a higher binding energy. So since the 1s subshell is full and the closest to the nucleus, it's going to be the leftmost, and therefore it's going to require the most energy to remove. 2s2 will require comparatively less, that's why we move to the right. And then the 2p subshell is the rightmost, because since that contains the valence electrons, it will require the least energy comparatively to the other subshells to remove electrons. So as you can see, the 2p subshell requires about 1 megajoule per mole, while the 1s subshell requires like a bit less than 100 megajoules per mole to remove the electrons from there. Now let's look at nitrogen's chart. It's the same thing, except nitrogen has 1 less electron, so the only difference is that the electron configuration is 1s2, 2s2, and 2p3. So again, the leftmost is the 1s peak because, as I said, the closer you are to the nucleus, the more energy is required due to a stronger force of attraction between the electrons in the nucleus. And then the 2s is relatively less than the 1s peak in terms of energy, ionization energy, and then the 2p peak is the rightmost, as it requires the least ionization energy to remove the valence electrons from the 2p peak. So yeah, you want to really get used to the terminology of ionization energy. Alright guys, so another skill I think that is important for this unit is identifying when there's been a jump of electrons from one shell to another. And to do this, you're given questions like the one I'm looking at right now, where you're given a table with ionization energies and the number of electrons, and all you want to do is look out for a big jump in ionization energy. So basically in this case, we have the first 2 electrons which have like a semi-low ionization energy, and then you jump to 501 on the 3rd electron, and that is symbolic of you going down in energy level. And just to be clear and explain again, an energy level, like treat each circle here as an energy level, and you're going down in energy level from the outer one to the inner one. All right. And basically, I know this because as we discovered earlier, the farther away you're from the nucleus, the weaker the Coulombic forces of attraction, and therefore the lower the ionization energy. So a quick increase in ionization energy is a clear indicator that you're moving closer to the nucleus, and therefore you're going down in energy level. And in this case, since the first 2 electrons are relatively low and then we jump up to 501, we can tell that this element or this atom in question has 2 valence electrons. Since those are the 2 that have the relatively lower ionization energy, you can be asked a similar question where you're asked to determine what element is being represented, and in order to do that, you go through the same steps. You determine the number of valence electrons, and then you just find whichever one of the answer choices aligns with an element on the table that has the same number of valence electrons. Now, Coulomb's law, we should have gone over this earlier, but Coulomb's law is basically a law that talks about attraction between 2 entities and how the 2 factors that affect that are distance and charge. So the greater the difference in charge between 2 atoms or entities, the greater the force of attraction, and the farther the distance between them, the lesser the attraction. So basically, Coulomb's law states that if you want to increase attraction, you either need to be really close to each other or you'd have a very high difference in charge. Now, there are 4 periodic trends covered by AP Chemistry, and I would really recommend not memorizing them, but rather understanding the reasoning behind why they work the way they do, as it's really helpful in reasoning out questions on many FRQs on the AP test. So the first one is atomic radius. It increases as you go down the periodic table and decreases as you go across. So as you move across the periodic table, you're maintaining the same number of shells of electrons. So you just have one, or two, or how many ever shells of electrons. But the number of protons is increasing. So this increase in protons means an increase in charge. And an increase in charge of the nucleus means an increase in the difference between the charges of the nucleus and the electrons around them. This causes for Coulombic forces to increase, and therefore for them to be grow closer as we move from left to right. That is why it increases as, that's why atomic radius decreases as you move across the table. When you move down the table, the reason that atomic radius increases is that you are maintaining the same number of protons, but you are increasing your shells of electrons. And this causes for the distance between the valence electrons and the nucleus to increase, which causes for Coulombic forces to grow weaker and therefore increase the atomic radius. Next is ionization energy. And as you move from left to right, the ionization energy is going to increase because, as we mentioned earlier, increasing protons and a constant shell of electrons causes for Coulombic forces to increase. And ionization energy is the amount of energy you need to remove valence electrons. So to counter such high Coulombic forces, you need more ionization energy to remove the electrons, which is why it increases. When you go down the periodic table, the ionization energy is going to decrease because, as we talked about earlier, the distance between the nucleus and the valence electrons is going to increase as you go down the table. And that causes for weaker Coulombic forces and therefore less ionization energy to remove the valence electrons. Thirdly, we got electronegativity. Now, electronegativity is just how likely is an atom to take an electron? How likely it is to do that. So one fact you need to know is fluorine is the most electronegative element on the entire periodic table, and it increases as you go across the periodic table and decreases as you go down. So one way you can think about this is like the closer you are to fluorine, the more electronegative you are, the farther you are, the less you are. And another way to think about it is that as you move towards the right of the periodic table, you get closer and closer to a full octet of electrons. And every atom and element on the periodic table wants a full octet of electrons because that is the most stable form for any element to maintain. And therefore, the closer you move to the right, the closer they get to that. And therefore, the more they want that electron to reach a state of stability. That is why as you move from left to right, the electronegativity is going to increase. But when you go down the table, it's going to decrease because you just keep increasing the number of shells, but it does not affect how stable the element is. Finally, we have electron affinity, which is the amount of energy released when you add an electron to an element. Now, this is one they don't go too deep into, and you don't really need to know any specifics, but just know that chlorine is the most electronegative element, and as you go across the periodic table, it's going to increase, and as you go down the periodic table, it's going to decrease. And the closer you are to chlorine, the more higher the electron affinity, the farther away, the less electron affinity. This says electronegative element. I meant to say electron affinity, my bad. Finally, we have ionic compounds. Ionic compounds are basically formed by ionic bonding, which is where instead of sharing electrons, like instead of covalent bonding, one atom will just completely give its electrons to the other one. So an example is salt. So remember how we talked about how every atom wants to achieve a state of stability by filling its entire shell of valence electrons? Well, chlorine has 7. And when it bonds with sodium has 1. So it just takes the electron from sodium, so it has a full octet of electrons, and then bonds with sodium. So this way, chlorine reaches like a stable form and it's bonded to sodium. They form between metals and non-metals, ionic compounds, which is not something you really need to know, as bonding is something we're going to go into more depth in future units. And one final thing to keep in mind is that ionic compounds, it always comes down to charge. So as you can see on this table, it has labeled the charges of like each specific column of elements on the table. So it goes +1, +2, +3. This says X, but it's +4 or -4. It depends on the scenario, which is, we'll discover many scenarios in the future, and then -3, -2, -1. So the most likely ionic bonds are going to form between two elements that have completely opposite charges. So that's why chlorine and sodium bond, because the -1 of chlorine neutralizes the +1 of sodium. And similarly, sulfur and magnesium could bond. The -2 of sulfur cancels out the +2 of magnesium. One final thing I'm going to mention is that many a times, if the charges of the two elements bonding are like the same, they can have similar properties. So one example is how sodium chloride, sodium having a charge of +1 and chlorine having a charge of -1, can have similar properties as potassium chloride, with potassium having a charge of +1 and chlorine having a charge of -1. Same applies for lithium chloride, as I've given as an example. Thank you so much for watching my video. If you have any questions or comments, please leave them down in the comments. And yeah, I am planning on posting a lot of videos on every unit to serve as a crash course for you guys to watch, like before a test or something, or maybe before the AP exam. So thank you for your time and have a great rest of your day or week. Bye.